Hello everyone, my name is Yuting Wang. Today I'm going to introduce the electron reduction of CO2 catalyzed by cobalt and nitrogen dope carbon materials. And this is the outline. We will start from the introduction and discuss the experimental section. And finally is the result and discussion and then the conclusion. As we know, the electrochemical CO2 reduction reaction is a highly promising technology. By using renewable energy, we can convert CO2 into valuable carbon-based product, effectively closing the carbon cycle. And in this research, we will focus on the production of syngas, which are CO and hydrogen. Syngas is an essential industrial feedstock for C1 chemistry. Traditionally, syngas is produced from non-renewable fossil fuels. Therefore, developing a method to produce syngas with tunable CO hydrogen ratio via electroreduction can help address the energy crisis. And however, there are two major problems in CO2RR. First one is high overpotential, because activating CO2 to form a radical anion requires a huge amount of energy. And second one is the hydrogen evolution reaction, which is a competitive reaction. Because in aqueous media, it happens very easily and compete with CO2RR, making it difficult to control and the final product ratio. Therefore, the core challenge is how to address the rate determining step to favor CO2RR over the HER. And to solve this, the researchers used ZIF67 as a precursor. ZIF67 is a type of zeolitic imidazolate framework that provides a porous structure and homogeneously dispersed cobalt species. By pyrolyzing ZIF67 at temperature between 600 and 1000 Celsius degree, we obtain cobalt at NC materials. However, a common problem with pyrolyzing is that metal species tend to aggregate, existing in various sites that are not benefit for our target reaction. And this is the most critical part in the study. Through the investigation, the researchers identified the role of different cobalt species. And first one is the surface exposed cobalt. This species mainly promotes the HER process, which we want to inhibit. And second one is the packaged cobalt, which is encapsulated by NC skeleton. These species act as electron donors, transferring electron to CO2 molecules through the cobalt NC skeleton, thus promoting the CO2RR. And the next thing is pyridinic nitrogen. These atoms are responsible for the absorption of CO2 molecules. And now let's move on to the experimental section. The synthesis of the cobalt at NCX catalyst following a two-step process. First, the ZIF67 precursor was synthesized by mixing cobalt nitride hexahydrate with 2-methyl imidazole in aqueous solution and stirring and keep for 6 hours at room temperature. And finally, will resulting in a purple precipitate. Second, these ZIF67 materials underwent pyrolysis under a nitrogen atmosphere. We test 5 different temperatures ranging from 600 to 1000 Celsius degree. We name this sample as cobalt at NCX, where X is the temperature. And to find the active site, we perform a rigorous acid treatment. The pristine materials were stirred in aqua regia at 60 Celsius degree for 4 hours. This process was repeated 3 times to ensure the complete removal of any surface cobalt species. And that is because the remaining surface cobalt species might trigger the HER. And we will label this acid treat sample as cobalt at NCXA. And to verify our results, we employed a comprehensive characterization techniques. We first use XRD and Raman to examine the crystalline structure and carbon defects, and SEM and HRTEM to see the morphology and confirm that cobalt was dispersed correctly within the nitrogen-doped carbon skeleton. And we will perform H2 pulse chemisorption to measure the surface characteristic of catalyst. This helps us understand how the acid treatment effectively reduces the affinity for hydrogen, which is the key to inhibit the HER, and then enhancing CO2 reduction performance. And finally, we will describe the electrochemical measurement protocols. We conduct the CO2 reduction experiment in a gas-tight two-compartment cell separated by naphthalene 115 membrane. First, we use a standard-free electrode system. We use a platinum plate as a counter electrode and silver chloride electrode as a reference, and carbon fiber paper loaded with our catalyst as a working electrode. And all these measured potential were converted to reversible hydrogen electrode, which called RHE. And we were using the standard Nernst equation to make a conversion. And then the CO2 gas was continuously delivered. The gaseous product was analyzed every 30 minutes using GC, which is equipped with TCD and FID detector. And we will calculate the Faradaic efficiency using the equation 1, which accounts for the number of the electrons required for each product molecular. And the CO productivity was also calculated and normalized by catalyst mass. And next part is result and discussion. And we can see figure 1. In image A, it is a SEM image of CIF67. The structure is rhombic dodecahedral, which means we successfully made the CIF67 precursor. And the pyrolysis process of CIF67 is studied by TGDSC profiles under N2 atmosphere. And in image B, there is a sudden weight loss with an endothermic peak at about 550 Celsius degree, which is mainly caused by the decomposition of CIF67 framework, which means the 2-methyl imidazole is decomposed to NC skeleton, and the cobalt-2 is reduced to cobalt-0. And the weight loss above 600 Celsius degree is gradually stable, which indicates that CIF67 has been almost completely pyrolyzed. Therefore, the temperatures from 600 to 1000 Celsius degree are chosen for the pyrolysis of CIF67. And in image C, it is a XRD patterns of CIF67 in different pyrolysis degree. And we can see 600 and 700 Celsius degree exhibit weak diffraction peaks in the range of 10 to 80 degree, which means cobalt species are highly dispersed. And however, As we increase the temperature from 800 to 1000 Celsius degree, we see a sharp peak at 44 and 52 degrees. And by using the Schur formula, we calculate that the cobalt grain size grows significantly from about 8.4 nanometer to over 34 nanometer. And this confirms that high temperature leads to the aggregate of cobalt particles. And in terms of the carbon structure, Raman spectroscopy results in image D, and show that the cobalt at NC700 sample has the highest ID-Ig ratio. And this indicates that a high concentration of disordered carbon and defects, which often correlates with a better catalytic activity. Okay, next, let's look at the figure 2, and let's see the morphology under the microscope. As shown in the image A to D, the original polyhedral shape of CIF67 is well preserved at 700 Celsius degree. But however, as the temperature rises to 1000 Celsius degree, we see significant aggregation, where cobalt species assemble into large, bright particles on the surface. To get a closer look, we perform HRTM in image F. We can clearly identify the crystal lattice of the cobalt particles with a spacing of the 0.202 nanometer, confirming the metallic cobalt 111 phase. And in figure 3, to understand the chemical state on the catalyst surface, we perform XPS characterizations. As shown in the survey spectra in image A, signals for cobalt, nitrogen, and carbon are clearly present across all samples. And if we look closely at the cobalt 2p spectra in image B, we can see two distinct peaks. The peaks at 778.2 eV represent metallic cobalt, while the peak at 788 780.8 eV is assigned to the cobalt NC species. The shift in binding energy suggests an electron transfer from the cobalt core to the nitrogen atoms through these chemical bonds. And in nitrogen 1s spectra in image C, we identified paradigmic nitrogen at 398.7 eV and the cobalt NC bonds at 399.6 eV. These are the active sites responsible for CO2 absorption and electron activation. But however, there is a clear trend. As the pyrolysis temperature increases, we can see that the intensity of the nitrogen signal drops significantly. The loss of the nitrogen weakens the interaction between the carbon skeleton and the cobalt particles. And without enough nitrogen to anchor them, the cobalt species aggregate into larger particles, which is why the 700 Celsius degree sample with a higher nitrogen content maintains a more optimal structure than 1000 Celsius degree sample. Okay, now let's see the catalytic performance through the LSV. Under the agar atmosphere, there is no carbon to react, so it typically produces hydrogen, which called HER. So to confirm if our materials are active for CO2 reduction, we compare their performance under agar and CO2 atmosphere. For a sample polarizing between 600 and 900 Celsius degree, we observe a trend. The onset potential is lower and the cathodic current is obviously higher in the presence of CO2. And for cobalt at NC700 in image B, the current density increased from 1.7 to 2.7 at the potential of negative 0.57 volt. This gap between the red and black curves means that it is an efficient CO2RR catalyst. Okay, and in figure 5, let's look at the actual product. As shown in the image B, CO and hydrogen are the only products, while cobalt at NC700 shows the best CO selectivity at the 33%. And we notice that at higher temperatures, like 1000 Celsius degree, the HER dominates, reaching a ferritic efficiency of 92%. This confirms that large exposed cobalt particles are selectively active for HER. And in image C, the author measure the TEFL slope. This value tells us that the rate determining step is the first electron transfer to CO2. So the key to better performance is enhancing these electron transfers while inhibiting the competing reaction. So the author used acid treatment, using aqua regia to remove the exposed cobalt particles that cause HER. And in image D, the H2 chemisorption signals completely disappear after the treatment, proving that the survey cobalt is gone. In figure 6, we can see the XRD pattern. The cobalt diffraction peaks obviously weakened, especially for the high temperature samples like 1000 Celsius degree A. This is because their large particles were mostly exposed and easy to be moved away. And the Raman results in image B show that an increase in the graphitic carbon ratio after the acid treatment. This means that the aqua regia selectively removed the more reactive, disordered carbon, leaving a more conductive and stable graphitic framework. And for morphological observation by SEM and TEM image, show that the surface cobalt particles had been mostly removed. This is further confirmed by the XPS spectra in image E. The peak at 778.2 eV, which representing metallic cobalt, drops sharply after the acid treatment. This directly proves that the exposed active site for HER have been successfully eliminated. And finally, let's look at the result of our acid treatment. We can see that the current density increased across all samples, and the stability also increased. Cobalt at NC700A was significantly improved over 5 hours of operation. And for the best sample, the ferritic efficiency for CO increased from 33% to 60%, while the hydrogen production dropped from 65% to 40%. And this confirmed that by removing the surface cobalt, we have successfully improved catalytic activity for the CO2 reduction. And the TEFL slope decreased to 112.2, indicating a faster first electron transfer to CO2. And in image E is the adsorption behavior changing of the CO2. And before the acid treatment is the black line, there is a step increase at low pressure region, which means it is a CO2 chemical adsorption. And the vanishing sharp step on the red line is the final proof that the survey exposed cobalt particles are gone. And we can see the picture. The picture is about before and after the acid treatment. We can look at the left side of the picture. It is the original cobalt at NC700. There are two competing pathways, and the yellow cobalt nanoparticles on the surface are highly active for HER. As we can see, water or photons interact directly with these exposed sites to produce hydrogen. And this is our rate determining step for the unwanted side reaction. And after the acid treatment, we can see that these surface exposed cobalts are removed. This effectively inhibits the HER pathway. And the remaining cobalt species are those highly encapsulated within the nitrogen-doped carbon skeleton. They transfer electrons through the cobalt NC skeleton to the surface. On the surface, pyridinic nitrogen species play an important role by absorbing CO2 molecules. And to conclude, this study successfully demonstrates a strategic approach to optimizing cobalt at NC catalyst for CO2 reduction. As we can see in the image A and B, our optimized cobalt at NC700A achieved its best performance at the mild potential of negative 0.57 volt, which turned the CO hydrogen ratio from a hydrogen rich to a carbon monoxide rich. And in the picture C, the 10-hour stability test in the catalyst show that zero significant decay. This confirms that the chain effect of the NC shell successfully protect the active center and produce high-quality syngas. Thanks for listening.